So actually the choose your own adventure part is not starting yet because I forgot to show you a little bit more detail about the example that I'm going to do, just so you can see a way of comparing the results from the code with the theoretical results. So here's the example I'm going to look at, and I described it as this contrived system where it's like population growth, but also people are dying at some linearly increasing rate. And this is so let's just solve this, since we can, let's just solve this analytically. So it's a linear differential equation, which you can see if you write it in this form. Then you've got this integrating factor, e to the minus rt. So that's pretty easy to get integrating factor. You multiply the whole thing through by e to the minus rt, and you get this. And then the left-hand side is this product rule. Then you integrate both sides, and you get plus c. Then solve for x, and this is your general solution. Okay, so you can pause and look at the individual steps if you want to, but it's not super important. I just want to show you how I got to some kind of plot before I do any numerical work. So here's the differential equation, and here's the solution just copied down, the general solution. Now to do numerical stuff, I'm going to need to put in specific numbers for the r, and I'll need to pick a specific initial condition. So I chose 3 for r. So 3 is like the population growth rate or something without people getting eaten or whatever this is. Then I chose the initial condition x of 0 equals 1/2. So that doesn't mean half a person. I get, maybe x is measured in millions of people or something like that. So this is 500,000 people, maybe. Then you can use the initial condition and figure out what the c here, the constant here, should be. And so I got this in the end. 1/9 plus 1/3 t plus some number times e to the 3t. Okay, then I can go to Mathematica and plot that, and I get this looking curve, which looks like an exponential growth curve, which I guess is not too surprising since the model is like the exponential population growth model, but with linear, with x prime also sort of decreasing at a certain rate, but not in a way that, well, let me put it this way. If x prime decreases at a rate of t at time t, like say we didn't have this term, then it's the same as the differential equation for like a falling object or something, with constant acceleration. So it's like x is decreasing at a rate which is itself changing linearly. So what would that end up doing? It would make x change quadratically, which is not going to beat out exponential growth. Exponential growth sort of beats all kinds of polynomial growth. I don't know if that's a very good way to reason through it, but for some reason that makes this plot make sense to me. Okay, so anyway, now we have a plot, so let's start looking at numerical ways to generate a plot without having a solution. So without having this, we're going to generate plots using the Euler method. Okay, and the next videos will be the choose your own adventure part.